Okay, so today I want to do sort of two topics, and there are really two examples in Galois theory. So first, we'll do sort of the easier one, the Galois theory of finite fields, which we've basically already done. But so this was recasting some things we've already talked about, and then also we'll talk about cyclotomic polynomials / extensions. So so you can tell I'm sort of rusty at how you can make tech look good when you're doing it ad hoc. Okay. Anyway, so that's what we're going to cover. And so cyclotomic polynomials, those are polynomials whose roots are roots of unity, in particular primitive roots of unity, and they sort of end up being irreducible and give you some sort of nice extensions of the rational numbers. So that's what we'll be talking about in that example. But first, the Galois theory of finite fields. So, okay, so let me just state the result. So I'm going to let FQ be a field with Q equals P to the N elements, and then take just a degree K extension. Let's call F that extension. So I know there is such an extension, and it's unique. And why do this is a little bit of a generalization of what we discussed before, and this is just the unique field with unique field with Q to the K elements, which is P to the N times K elements. And so it's not so hard to show that the field with Q to the K elements contains the field with Q elements. So let me, I think, I can't remember if we got to that last time or not, but let me just state it as an exercise, and we'll, and if you don't know how to do it now, you'll know how to do it by the end of what I finish saying. So if this is terrible notation. All right, FP to D is contained in FP to K if and only if D divides to K. So let me write this here, lest it be preserved for posterity. So of course, I mean, FP to D is not a thing. I hate this notation. So like the way, okay, so this notation, like the way I used it here, I said let FQ be a field with Q equals P to the N elements. That's fine. But often people use the notation FQ as if like there's a distinguished field with P to the N elements, and there's sort of not. There's no distinguished construction of a field with P to the N elements. So I mean, one way to pin down a field with P to the N elements is to sort of fix an algebraic closure. So and the point is, in the field with P to the N elements is unique up to isomorphism, but that isomorphism is not unique. Like, there are multiple choices of isomorphisms. So, and like there's no distinguished construction of it. So when you just say the field with P to the N elements, like there's not really a V field with P to the N elements. So one way you can make sense of this is sort of fix an algebraic closure. FP. So FP makes sense. There's a single field with P elements. It's just d mod pz. Like there's no, there's a distinguished field of p elements, and sort of only automorphism is a trivial automorphism. So somehow like it makes sense to say that the field with p elements. So I can take the field with p elements, and then I can take a algebraic closure of that field, and that's a choice. So making that, like choosing an algebraic closure is a choice, but somehow it's making all of the choices I want to make at once. Then sort of define the f p to the k to be the splitting field of x to the p to the k minus x over the fp in this algebraic closure. And probably you guys are sick of me harping on this kind of point, but and this is really important. And this is really important. It's not emphasized enough, and it's a common way of getting confused is sort of thinking things make sense that don't make sense without sort of doing some auxiliary construction to make them make sense. Okay, so so this is sort of a way that this sentence then makes sense. That fp to d is contained in fp to the k if and only if d divides k. Now, like I sort of made sense of this by fixing an algebraic closure and then sort of declaring sort of fp to k to be some specific field, subfield. And this solution also, like to making sense of this, sort of looks a little bad because I mean, if in general, if you say fix an algebraic closure of something, that involves the axiom of choice, which, well, you don't really want to use the axiom of choice to make an algebraic closure. Luckily, to produce an algebraic closure of fp bar, you don't need the axiom choice. Right? So let me say, here's another exercise. To sort of produce, so produce an algebraic closure of MBBFP without using axiom of choice. So here's a hint. Look at splitting fields of x to the p to the n factorial minus x. Sort of as n increases. So sort of like look at the splitting field of like x to the p squared minus x, and then so that's 2 factorial, and then take sort of the splitting field of x to the p to the 3 factorial over that, and so on. So this will give you a tower of extensions whose union will be algebraically closed. Tower extensions whose union is algebraically closed. So it's not as simple as just saying, okay, let me fix a splitting field of x to the p, like x to the p to the k minus x for every k, and then sort of taking some union of those, because those aren't naturally contained in each other. So, and the subtlety here is like you have to sort of make some larger and larger field that's sort of containing these sort of smaller finite fields in such a way that sort of every time you enlarge, the one is always contained in the next one. Okay, so anyway, so that's sort of some things you can think about on your own, just to clarify your understanding. Let me go back and try this one again. So let me just copy this line that I had before down. Okay, now FQ is a field with Q equals P to the n elements. And then I'm looking at some degree K extension of this. Then call the theorem. The Galois group, well, let me say it this way. First, this is a Galois extension, and with Galois group Z mod KZ generated by the Frobenius automorphism. Here, I mean the Q power Frobenius. Which sends sort of any element to its Q power. So okay, so what does this mean? Well, when I say F over FQ is Galois, if Galois group is Z mod KZ, that means sort of I have some I'm saying there's some isomorphism. Really, and here I'm saying there's a canonical isomorphism from Z mod KZ to this Galois group. And sort of what does that mean? I mean, that means I just have to give some element in the Galois group that generates it as a cyclic group. So I just have to say where one goes. Maybe let me say that again. The map from Z mod KZ another way to phrase what I just said, maybe more precisely, there's an isomorphism from Z mod KZ to the Galois group of F over FQ, sending 1 to prob Q. Okay, so I mean, okay, so let me ask you a question before I prove this. Well, okay, for step one, why can someone tell me why this extension is Galois, just with sort of no, without sort of computing anything about automorphisms? So let me ask a simpler question. Can anyone tell me how many elements are in F? Okay, good. So someone wrote the answer to the first question. Which separable polynomial? So someone said you can just write Galois by showing it's a swing field of a separable polynomial. I think, and we have a head shake, so maybe we don't know, or maybe we're working on getting there. Okay, so anyway, oh, you can't type it. That's also difficult. Yes. Yes. So what is D? Yeah. So it's well n times k, because F has degree as F has so Galois, because it's a splitting field of x to me just write it this way. It's not, and again, I caught my own trap. It's a splitting field of this. So x, and this is x to the q to the k minus x, x to the p to the nk minus x. Okay, and then this is how we sort of constructed finite fields and sort of what we sort of, and we know that any finite field of order p to the p to some power is sort of the splitting field over fp of that polynomial, but sort of it's then the splitting field over any sub-extension as well, that polynomial. Okay, good. So this is sort of one way you can see that it's Galois. Good. We don't need to do this because you can actually sort of. So this is not necessary for the proof, but it's a good sanity check. Okay, so let's move on to the proof. So, and the claim is we just need to check that the order of prob Q is K. So why? Well, let me say two things. We need to check one. I guess before we check it, we should check that prob Q. Like, so I just wrote this thing down. I didn't really justify yet that it was in the Galois group. I mean, there's something to say there, and there's something to just make sure you understand there, because like it wouldn't be true if I wrote like the p power Frobenius. So, and I know it's a field automorphism. You know, I know it's a field automorphism because it's just sort of iterating, and I know the p power Frobenius is the field automorphism. I know it's just given by iterating the p power Frobenius. But the elements of the Galois group of f over fq are not just field automorphisms. They're field automorphisms that fix fq. But I mean, so but x maps to x to the q like definitely fixes MBFQ. So to justify one, because sort of the elements are the elements of FQ are exactly the roots of x to the q minus x. So saying your root of xq minus x is saying that x to the q is equal to x. Which is the same as saying that the Frobenius q of x is equal to x. Okay. So, and of course, and this, and again, let me just highlight, or like there was something to check here because the p power Frobenius is an automorphism that doesn't fix all of fq. Like, and if q is p squared, then the p power Frobenius wouldn't fix fq. So you do have to check something. And for two, well, definitely, sort of by the same argument, prob q to the k, which was just prob q to the k. So if I iterate prob q k times, this is just raising everything to the q to the k power. So this is tech issues. So this is raising everything to the q to the k power. This is the identity on and for the same reason. With q to the k. I mean, the point is the elements of this field with q, and the field with q to k elements is the splitting field for x to the q to k minus x. And so that's the same, the fixed points of Frobenius. Okay, so this, let's say it's the identity map. Okay, so this is this gives you the order divides K. On the other hand, like if sort of from Q to the D equal, which is just the same as from Q. So if there's sort of some smaller number, such that this is equal to identity. Sorry, I'm computing the order, so I'm just computing the smallest number such that this, if I compose this myself d times, I get the identity. And so if I have some smaller number, then everything in F satisfies Q to the, satisfies X to the Q to the D minus X is equal to X. And that's what it means to be fixed by the Q to D power Frobenius. But there are only Q to D roots of this. So that's not possible. In F. So F is Q to the K. The size F is Q to K is greater than Q to D. So it's all, and everything in here is all the same argument. Okay, so good. So I've sort of checked my things that I said I needed to check. Can someone tell me why these two things were all I needed to check? And so this shows that sort of the Frobenius Q generates a copy of D mod K Z. So it generates a subgroup, isomorphic Z mod K Z, inside of automorphisms of F that fix FQ. So what do I need to, why do I know these are equal? Yeah, great. So it's just posted in the chat. So, and the reason is we know that for any field extension, the size of the automorphism groups is at most the size of the extension, or is at most the degree of the extension. And with equality, if and only if it's Galois. So this was, I'm saying that the size was equal was a characterization of being Galois, being a Galois extension. But to show, and this is something we sort of mentioned last time and sort of harped on a little bit, let me harp on it more. And when you're saying you need to prove the size is equal, really you're trying to prove there are enough automorphisms. You always have, there are fewer automorphisms than the degree. So you just need to show that you really have at least K like at least that many automorphisms. That's exactly what we've done. So we've shown there are K automorphisms where K was the degree. And so we get this copy of Z mod KZ inside of here. So the subgroup generated by the Frobenius AQ, which was identifying with Z mod KZ. And so in Z mod KZ, like you can sort of think of it as, and you should think of this group Z mod KZ as being code for a cyclic group of order K with a distinguished generator. And so here, this Frobenius AQ is this distinguished generator. This is equal to okay, so that's the result we want. Right, so in this inequality is really nice. I mean, somehow you'd be, it'd be a real pain if every time you were sort of trying to show something was Galois, you had to like, it'd be a real pain here if we then sort of had to like go through and write out the argument that there couldn't be any other automorphism. And you could just write out explicitly an argument there couldn't be any other automorphisms here, but I mean, it wouldn't be as short. So it's very nice to have this sort of general fact that you just need to produce enough automorphisms. You don't need to sort of rule out sort of more automorphisms. Okay, so this is the simplest, this is the simplest Galois extension. Sort of any extension of finite fields is Galois. And sort of the Galois group is just sort of cyclic of the order. So let me sort of just state that as a sentence to remember. Any extension of finite fields is Galois with Galois group generated by Frobenius. So that's what we've shown. Let me say cyclic generated by Frobenius. And this is a very unusual setup. I mean, so like on the homework and probably before this class, you've seen examples of like extensions of the rational numbers that are not abelian. Sorry, that are not Galois. And you should not in general expect all field extensions to be Galois of a given field. Let me just, so it's quite unusual to have a field such that all of its extensions are Galois. So an equivalent, yeah, let me not say, let me just say an exercise. If there is a polynomial in K of X, so f of X, coefficients of K, whose Galois group is not abelian, then there is an extension that's not Galois. And this isn't a thing about separability. Like, and this is sort of the other thing you could be worried about. It's like sort of, and this is sort of about things not always being sort of splitting fields. So this sentence I just said is a pretty straightforward implication of the fundamental theorem. Okay. Good. So, I mean, that's what I wanted to say about the Galois groups of finite fields. You might think that this is just an example. When you first see this, you might say, okay, this is an example and it's very nice and simple, but it's just an example and we're never going to come back to it again. Let me dispel that notion from your head. You'll see it when we're already going to come, and we're going to come back to it immediately when we're doing cyclotomic fields, cyclotomic polynomials and cyclotomic extensions. But like more than that, and somehow using extensions of finite fields is like a crucial way of how you can sort of compute Galois extensions in general, like you compute Galois groups in general. Like if you want to give an algorithm for computing Galois groups, or that algorithm uses finite fields. And somehow in in sort of number theory and sort of the way Galois groups arise in sort of number theoretic problems, like the fact that you have sort of these, somehow the fact that a finite field has a Galois group of a distinguished generator is like an incredibly important and elementary fact to like how all of modern number theory is set up. So like this is sort of not, even though it's sort of a simple example using like fields that you don't necessarily think of as being like the main fields of arithmetic interest, this is like an absolutely central computation to modern number theory, for example, and to other areas too. So maybe I'll add that to my sentence to remember. Okay, so I'm a number theorist, so of course I care about these things. I would argue even if you're not a number theorist, you should probably care, because it's related to other interesting things like in topology and so on. But well, anyway, stop there, and I'll move on to the next thing. Okay, so good. That was a page, so we'll make a new page. Let's see. Let me set up so now we find out if I can scroll to the next page. Yeah, and so for anyone who missed this at the start, if you're wondering, I broke my Apple Pencil and I'm waiting for my replacement. So that's why this is being texted today. Okay, good. So the second page. Okay, so the next topic is cyclotomic. Whoops. Okay, so this is again going to be a basic example that also happens to be of central importance in number theory, but sort of where you can sort of understand something and compute the Galois group. And and even to sort of do this computation, though, we'll have to use finite fields. Okay, so let me write down a definition. Oh, I think I wrote it down earlier, so I can just copy it. Great, good for me. Okay, so this is a definition of this is one possible way of defining a cyclotomic polynomial. So this is in this is called polynomial a priori with coefficients in complex numbers. So this is the nth, I'll put that label above it, the nth cyclotomic polynomial. This beast. And so what's the important thing about it? The roots are the primitive nth roots of unity. So in the complex numbers. Okay. And so right now in the complex numbers, but sort of in a second we'll see like this actually makes sense over any field. So what do I want to say? Yeah, and so it's like this is an explicit formula. So we've already seen all these things are nth roots of unity. So e to the 2 pi I k over n, and they're primitive because whoops, my parentheses in the wrong place. And they're primitive because I'm taking elements of Z mod NZ cross. So if I take e to 2 pi I k, where k is a unit in Z mod NZ, then I get sort of something whose nth power is so primitive means zeta to the n is equal to 1, but zeta to the k not equal to 1 for, let me say zeta to d is not equal to 1 for d dividing. So let me give a different definition of this polynomial, from which we can see that it has integer coefficients. So this is the GCD of x to the GCD of, sorry, let me say it this way. It's going to be, I take x to the n minus 1. So I take the thing that has all primitive roots of unity, oh, sorry, all nth roots of unity as its roots. And I divide it by sort of anything that's divisible by a small, like I divide by all of these smaller roots of unity. So let me just write this sort of compactly is I take the GCD of x to the n minus 1 and product over all. D divide n, d not equal to n. X to the d minus 1. That GCD just consists of sort of, it's just the product of sort of x minus zeta for all of the sort of non primitive roots of unity. And the reason I wanted to write it as a GCD, so is because that greatest common denominator is the greatest common denominator. And GCD of sort of two polynomials just means sort of the monic generator of the ideal generated by those two polynomials. So another way to think about a GCD. So and the GCD of those two polynomials has rational coefficients, but in particular, and it has integer coefficients because it's rational coefficients, but it also divides x to the n minus 1. And so and this is a polynomial of integer coefficients. And so, okay, so the result is a polynomial of integer coefficients. So I just wanted to sort of say this. You can check easily if these two definitions agree because you know sort of what the roots are of all these polynomials, sort of in the complex numbers. But this second expression gives you a way to see that this is a polynomial of integer coefficients. Okay, I mean, let me say another way to write it. Vn so now I can sort of inductively describe it by saying phi n of x. So phi 1 of x is equal to x minus 1. Then phi n of x is the product is x to the n minus 1 divided by the product overall, so d dividing n of, or now d is not equal to n, of phi d of x. So again, this is sort of apparent from the definition. I want to get only the primitive nth roots of unity. So, well, every root, like every nth root of unity sort of has some minimal power that's equal to 1. So any nth root of unity is primitive for some divisor d of n. So let me just sort of divide out by sort of the all of the smaller, sort of all the polynomials that have those smaller primitive roots of unity. And so I'm just sort of breaking up roots of unity into primitive roots of unity for sort of different degrees. And so if I sort of divide out by all smaller degrees, I'm just getting left with the and so this is an inductive definition because I've told you what phi 1 is, and then like one, and now that lets you this sort of, now for anything like any prime number, this tells you what x to the, what phi p is, and then okay, once you know for any prime number, then for any like product of two primes, this gives you it gives you that, and so on. So this is, and from this definition also you can see that it's contained in the integers. In fact, you can do a little bit better. So in the nice part, okay, so what's the nice part about having a polynomial with integer coefficients? Well, if a polynomial with integer coefficients, you can treat as a polynomial over any field. So if k is a field, the following is true. So if k is a field, then the roots of phi n of x are exactly the primitive nth roots of unity. I.e., the elements zeta and k such that zeta at n equals 1 for and zeta the d is not equal to 1 for the proper divisor of that's not okay, and then the proof is just apply the inductive definition. In everything that's a root of phi n of x sort of is a root of x to the n minus 1 of x, but sort of it can't be, and because you're divided out by sort of all these phi d of x. And so let me say, and prove it inductively by applying the inductive definition. So okay, and somehow, yeah, well, and I could have just started with this as the definition. I could have started with the inductive definition as the definition, but I sort of like starting with something concrete, like sort of using the complex numbers where I sort of have some explicit formula for these to see it a little bit more clearly. But the statement is true. In any field, so if I so let me say this a different way. So in particular, if the I'm trying to add to this lemma, if the characteristic of k does not divide, it's coprime to n, so it's the characteristic of k is a prime number. If that prime number doesn't divide n, then and sort of phi n. Okay, let me not try and say this like this. So, I mean, there's a little bit silly. Normally we talk about roots. Yes, let me just say something else and rather than what I was right. I mean, normally we talk about roots of polynomials with coefficients in k. So in the point when I say these are roots of phi n of x, like really, I mean, like I have a map from z to k. Like I always have a map from z to any ring. And so I can sort of take the polynomial phi n of x, and I can sort of just treat it as a polynomial, like I can get a new polynomial in k of x. So like if, So note if like K is equal to FP, then sort of phi n. So like then the image of phi nx in K is just given by reducing the coefficients mod P. And so in saying I have a root of phi n of x, it really means like when I can treat it as a polynomial in z brackets x or a polynomial coefficient z, or really as a polynomial with coefficients in K, just by sort of reducing it. And the point is, this is sort of completely unambiguous because there's a unique map from the integers to any field K. So when your polynomial has coefficients in integers, like it's sort of simultaneously a polynomial over every single field. So let me say that, in every single sort of field or even ring, because there's a unique map from Z to R for any ring R. I mean, just because once you say you send 1 to 1, then you know then you know everything about where this goes. Okay, so let me state the main result, and then we'll take a break, and then we'll come back and explain how to prove this. Let me say it this way. Is irreducible, and we know its degree, so the degree, just from our very first formula, we know the degree. So Z mod NZ. It's the size of the units in Z mod NZ. Which is just in this sort of Euler function of this thing just means the number of numbers less than n co-prime to n. All these are the same number. And if I look at Q and I join I add in primitive root of unity. I mean, it doesn't. So here it doesn't matter which primitive root of unity I take. I'd get the same field, but let me just take the simplest one. So it's a Galois, and moreover, there's a canonical isomorphism. So, and this word canonical is important. It means I'm not just saying it's sort of abstractly isomorphic to this group. I'm saying there's really, I'm going to write down a concrete, completely natural isomorphism. So an example of two groups which are not canonically isomorphic are Z mod P minus 1 Z and Z mod P Z cross. We know that Z mod P Z cross is cyclic of order P minus 1, but there's no natural choice of a generator. So they're isomorphic, but not canonically isomorphic. So when I say there's a canonical isomorphism, I mean, I'm really going to write down an isomorphism, not just prove that there exists an isomorphism, but not pick one out. And this is something that's also not highlighted very much in a undergraduate algebra class, but I mean, it's super important. So let me just say this. I mean, you want canonical isomorphisms when you can have them. If your isomorphisms are not canonical, they're not worth much. Sometimes they're helpful anyway, but you're always much better off if you have a canonical isomorphism. Somehow it's much more useful. So let me call this, and I'll write this map as n maps to sigma sub, or k maps to sigma sub k. So k is an element of z mod n z cross. And sigma sub k is going to be an element of this Galois group. And sort of the distinguished property of sigma sub k, when I apply it, is when I apply it to a primitive p fruit of unity. In fact, any p fruit, or sorry, any m fruit of unity. So in particular, that says what it does to this generator, either 2 pi I over n. So that definitely sort of this pins down what sigma k can do. But this is a little bit of a stronger statement because it says it deduces, sort of, once you know what it does to this generator, well, this thing sort of generate, like, powers of this are all the other m fruits of unity. So you can sort of deduce that it sort of does the same thing to any m fruit of unity, but sort of somehow it's nicer to write it down without sort of, and somehow it's nice to write this down without sort of distinguishing this m fruit of unity is the point. So there's nothing special about that m root of unity versus the other ones in this perspective. But anyway, so like definitely knowing what it does to zeta sort of pins it down. And of course, it is going to have to send zeta to some other primitive m root of unity. So like in knowing that all of the automorphisms are of this form is the easy part. Knowing that anything of this form gives you, like, that you can realize anything of this form as an automorphism is not trivial. So let me state that. So it's easy to see every automorphism must be of this form, but needs an argument to see that so there is an automorphism that does this. So I know every automorphism must send zeta to k, but I don't know that, like, for some fixed k, there is an automorphism that sends zeta to k. So let me start the proof and then we'll take the break. So let me sort of do a however. I do know the extension is Galois. And it's the splitting field of x to n minus 1. It contains all the m fruits of unity, and sort of any field that contains sort of a primitive m fruit of unity has to sort of contain all of them. So you can check this. And so I know that the size of the automorphism group, let me just write, sort of abbreviate just the automorphism group. So the automorphism group of this field extension. So this is the degree so I'm just getting tired of writing this field extension. I'm taking it out. And it suffices to show that the degree is the size of Z mod n Z cross. Because if I know every automorphism must sort of do like this has shown me that sort of I have at most phi of n choices for the automorphism, because every sort of one has to sort of send e to the 2 pi I. Like I know that every one of them has to send. Let me say it this way. I mean, I said this one way, but let me say it another way. And like we know that's e to 2 pi I over n is a root of phi of n, phi sub n. So we know sort of, and then every other polynomial, like we know it has to send it to sort of another root of phi sub n, and then but sort of it's completely determined by what it does to that. So sort of once you've said what it does to that, you're done. So that means there are only sort of phi sub n choices, at most phi sub n choices. And so if you can show that there are phi sub n, if there are phi of n automorphisms, then sort of all of these must, like all of these possibilities must rise. Okay, but so it suffices to show that the cyclotomic polynomial is the minimal polynomial of e to 2 pi I over n. So, and of course it's 0, so we just need to show that it is irreducible. So that's the whole thing. And this computation, the Galois group, just comes down to sort of spelling out what are even the possibilities for what an automorphism could do, and then seeing there aren't that many, and then just observing that like if you can prove that phi n is that this polynomial is irreducible, then like that computes to the degree, and sort of you're done. Okay, so the thing we need to prove then is that phi n of x is irreducible. Okay, so let's take a 5-minute break here, and then we'll come back at 1:30, and we'll in the last 15 minutes we'll outline this proof. Okay, yes, let me pause. Okay, so we'll get started again. So I corrected, or not corrected, but sort of just clarified the statement of this lemma. So the point is that this polynomial is irreducible as a polynomial in Qx, or sort of equivalently in Z brackets x. So polynomial coefficients Q or Z. And I wanted to be careful because I've already said you can sort of think of it, like for example, as a polynomial of coefficients in FP by just reducing the coefficients mod P. But well, of course, this will show up in the proof. But when you're reducing the coefficients mod P, like you're losing some information. So you can really make, and you can make the polynomial become, can and will make the polynomial become reducible by doing this. So before we do this, let's just do a quick example, because we've already seen this in at least one case. So if P is a prime number, let me say it, because I'm about to use P a bunch, and will sort of be in an orthogonal way. Let me say if L is a prime number, then, well, sort of phi L of x, so this cyclotomic polynomial, is, so you can't see that, then phi L of x, well, this is just x to apply the inductive definition, for example. It says x to L minus 1 over x minus 1. Well, this is 1 plus, this is x to 1 plus x squared, x plus x squared plus and so on, all the way up to x to L minus 1. And this is irreducible by Eisenstein's criterion. And after you make a substitution. I think that's the right one. I always get confused about what you're supposed to do. X is equal to y plus 1. Yeah, good. So I think this is, okay, sorry. So I apologize because I've started to get, I taught this class last spring too. And for the most part, the syllabus changed around. So for the most part, there wasn't overlapping material, but now we've started getting to the point where we're overlapping material I covered last spring, and also I'm covering this spring, and I'm starting to get a little bit turned around of like what we have and have not covered. Is this an argument that we've talked about before? Okay, good. So, okay, good. So if it's not one you remember, or not one you're familiar with, then just take a look at that, and then maybe go back and check that. So in this simple case where L is prime, it's easy to check this is irreducible. But in this Eisenstein argument doesn't generalize. Like it's not, these polynomials aren't Eisenstein for a composite n. So you really, and you need some other, and you need some argument, some more general argument for composite n. Okay, so I mean, there's maybe even like a sort of precise sentence you could say for why this doesn't generalize, but let me not. So let me do the proof of the lemma. So the proof that it's irreducible, I guess that's lemma 2. Oops, that's the one. But we're going to use this fun thing we noted before, that the roots of Bn of x in K, like in any field, that sort of are the primitive roots of unity. Let me explain how. There are different ways you can think about it. Somehow I've presented this proof before, and I don't think I've landed on the best way to present this proof. So sort of apologies in advance. This is how I do it, but I'm not totally satisfied with this as a presentation. Right. So let me fix some notation. So I'm going to write zeta is equal to e to the 2 pi I over n. And then I'm going to write z zeta subset for the sort of smallest, and for the obvious thing, for the smallest thing containing zeta and containing zeta and z. So small subring containing zeta and z. So obviously this is contained in Q zeta, but sort of just the things with integer coefficients, and really, and it is equal to since so if I write g of x for the minimal polynomial, over Q of zeta, then if I take an arbitrary element in Q, like this minimal polynomial might have rational or in C, this like an arbitrary algebraic element for Q, this minimal polynomial might have rational coefficients. But since it has integral coefficients, which I know because it sort of divides, it divides some integral polynomial, so it has integral coefficients. So since it has integral coefficients, then So since it has integral coefficients, then it's easy to check that z zeta is isomorphic to the polynomial rings with coefficients in x mod g of x. Okay, and so this is, you have to be a little bit careful doing this just to make sure, and this is okay, but this is only okay because the minimal polynomial has integral coefficients. Sort of you could get in trouble otherwise. But okay. Okay, and so, well now, okay, so I'm gonna look at I'm gonna do something that's going to seem kind of crazy. So I'm gonna pick a prime p, not dividing it. And then I'm going to look at z zeta mod p, which is just applying standard isomorphisms for taking quotients of rings. This is sorry, tech troubles. So I can think of G as being a call and just reduce the coefficients of G, and I get a polynomial over Fp of x. Okay, and well, so let me write overline. Maybe I'll write overline G for sort of where I reduce the coefficients on P. Okay, so I can do this, and okay, and then I'm just going to sort of pick irreducible factor of G bar. I'll call it sort of actually, let me say it this way. I'm going to pick an embedding. I'm going to pick a map. So you can think to an algebraic closure of FP. So you can think about this, but just choose an irreducible factor. Choose an irreducible factor of G bar. This will give you, and you'll be able to get a map like this. And sort of then choosing that, and so choosing an irreducible factor of G bar will sort of give you a map to a finite extension of FP, and then sort of just, and I could just work that finite extension, but let me instead just work with FP bar to really sort of, I'll say something's a little bit cleaner if I do this. And so then I'm going to get the following. I'm going to get some bijections between 3 sets. So in the middle, I'm going to put, so on the right, I'm going to put roots. So roots of phi n of x. Let's see. In the complex numbers. Okay. Well, all of those roots are contained in sort of this subring Z zeta. Let me say this, I get bijections. And then, well, now I have this map from Z zeta to FP bar. Like certainly if I have a root of this polynomial, in like Z zeta, then I sort of take this map to FP bar, like I get a root in FP bar. So and the right sort of equivalence is the right bijection, the bijection between the middle and the right set, like that's just because Z zeta is contained the complex numbers and it contains all the roots. This thing on the left is just, it's a computation, but the point is like I can write and this is just because in phi n of x equals the product of k in. It's because I have sort of, there's different ways to say this, and this is sort of one way to say it. So let me scroll down so you can see what I'm writing. Whoops. And because I have this factorization, which is sort of in Z zeta x. So I have this factorization sort of over this ring with coefficients in this ring Z zeta. And so that gives me, that gives me a factorization of this polynomial also in FP bar when I apply the map to FP bar. But somehow I know that, and this polynomial is separable, and because p doesn't divide n, this polynomial is separable. The already x to n minus 1 is. So the phi n is just sort of a factor of x to n minus 1. I could have just written x to n minus 1 everywhere here anyway, but so yeah, and somehow I could have. So I'm over time. But okay, so now it's just like an accounting argument. Like I know I'm getting sort of these zeta to k are going to the roots of this polynomial in FP bar, but I'm really hitting all of those roots. On the other hand, I know like that's how many roots I have. So in this map has to be a bijection. So this left-right inequality is a little less clear because like when you sort of apply this map to FP bar, like that map has a kernel. So a priori, like you're losing information. But it turns out if you apply this map to root, like you're not losing so much information that you can't tell apart roots of this polynomial. So with this map to FP bars can still distinguish all of the different roots of this polynomial. Okay. So now so this bijection sort of preserves roots of G. Like the set of roots of G is sort of preserved on this bijection. And so let me just I'll come back to this, I guess, on Tuesday at the start. So now you're going to use sort of something you know over over finite fields. You know that sort of if you have a root of a polynomial over a finite field, like, and this polynomial has coefficient, like G has coefficients fp brackets x. So you know if you raise it to a p power, you're going to get another root of that polynomial. So what that, if you sort of apply that you have a bijection here, and sort of this, and this tells you that any roots, like this, the same thing holds all, like the same thing is going to hold over already in z zeta, and that's all in the complex numbers. Like if zeta is a root, like if you have a root, if you have a root of G, then its p power is also a root of G. So, but now like this sort of applies for all p that don't divide n, and sort of all these elements p and these generate sort of z mod n z cross. So you'll get sort of any sort of power of zeta has to be a root. Any of these powers of zeta has to be a root of G, but that just means G is equal to phi sub n. So and this is like a wonderful magical argument where you go from something that in the complex numbers to something in like over a finite field, and you use what's happening over the finite field to sort of deduce something about what's happening over the rational numbers and sort of, yeah. I mean, it's, and I think the first time you see an argument like this, and maybe every time you see an argument like this, it's really a miraculous kind of way to think. So I enjoy this kind of thing. Okay, but sorry, I went over time. Let me stop. I will come back. I'll go over the end of this a little bit more carefully next time at the start of class.